So we're going to continue with our derivation of the wave equation using the equations we found last time, and now also using Newton's second law of motion, so F equals ma. And so in the present context, F here is going to be the net vertical force, and then the ma here is going to be understood as being the time derivative of momentum. So momentum is mass times velocity, and then we're going to take its time derivative. Okay, so let's look at the time rate of change of the momentum. So we'll take this one here. And write out an integral expression for the momentum of a small interval from A to B. So we will have, let's see, so there'll be the velocity component, and then there'll be the density going through here. And so we've got density rho xt times our arc length component. Dx. All right, so that'll give us the rate of change of momentum on the left, and then on the right we need to look at the net vertical force due to tension. And so at the left end point we'll have dBt, and this is the vertical component, so we multiply that by the sine. And then this differs, since it's net, by the force of the left end point. Like so. Okay, and then so by using the fact that the tangent is sine over cosine, I can multiply the right side by cosine over cosine and then factor it out. And this just will give us the tau factor that we saw before, multiplied by the difference in the tangents. So then in the next line, this becomes tau. And then what we saw before is that the tangent of theta is actually u sub x. So we have this expression. And by using the fundamental theorem of calculus, this gives us the integral from a to b tau t times second space derivative of x. And again, since this is true for any a and b, we can remove the integral signs, and we end up with, oh, I forgot to do something on the left-hand side. Yes, I did. Sorry, let's back up right here and recognize that, let's see, if we put the time derivative under the integral sign there, then I have that guy. And then we also saw last time that we can substitute this expression right here for the equilibrium tension. So let's do that as well. Okay, so that's what I should have on the right-hand side. Okay, so now comparing from the, on the left-hand side. So comparing between the left side there and the left side here, if we remove the integral signs, we get UTT is equal to tau over rho naught UXX. Okay, and notice that this coefficient guy that we got here, tau over rho naught, this, if we look at the units for it, so tau is a force, so it's mass times acceleration. So it's got units of mass times length over time squared. And then if we look at rho, rho is mass per length. So that's 1 over rho. And then there's like some cancellation of masses, and the lengths collect together and the times collect together. And that gives us length squared over time squared, which tells us that if we take the square root of that, it's length per time, or in other words, speed. And so typically C is a constant. And it's called the wave speed. And then the wave equation is the second time derivative of u being equal to c squared second space derivative of x. And so this is a very famous and very well-studied equation. The most common boundary conditions are homogeneous Dirichlet boundary conditions. So homogeneous meaning that they're set equal to 0, and Dirichlet meaning that it's the value of u and not, say, its derivative that's being fixed. So this is, I guess I'm assuming that this is for the interval from 0 to L. So for a vibrating string of length L, those would be the boundary conditions. And then for initial conditions, since it's second order in time, you would need to have some initial condition on u, and then also some initial condition on u sub t. And that can be whatever you like. It'll describe the shape of the wave that's traveling, because as the name might suggest, the solutions of this equation are waves. So in fact, if f and g are C2 functions, so f is C2 if and only if the second derivative is continuous. So if f and g are C2 functions and c is constant, the wave speed, then f of x minus ct and g of x plus ct will be solutions of the wave equation. And we'll also even see that any solution looks like a superposition of a right moving wave like u1 and a left moving wave like u2.